to our Geneva Drive Wheel CNC machining lab. Today, I'm going to take you through the process of CNC machining the drive wheel for the Geneva Drive Assembly. So remember, this Geneva assembly, when you rotate the Geneva Drive Wheel, it turns continuous motion into incremental motion. It's basically how a watch works, or the tool changers in the umbrella style Haas machine right here has a Geneva wheel inside of it as well. So when it goes ahead and it indexes the appropriate tool position, it can take that continuous rotational motion from an electric motor and turn it into incremental motion thanks to the Geneva wheel. So the first thing we always do is we look at our engineering drawing here for our Geneva wheel. And we talked about how we programmed this from CNC operation number 1 and CNC operation number 2 in our lab presentation series. So hopefully you've watched that and know where the 0 points are located. Remember, the work coordinate system is on the B datum right here for the XY, so that's where the 0 point is. It's in the center of the part, or the stock. And we put all of our Z0 points at the bottom of our job. So we decided to start off with 2.75 inch diameter stock. If you look, the major diameter of this part is 2.725. So we'll end up machining 25 thou off the outside edges, or contouring the outside edges of this part at some point. We will also use a face mill to qualify that surface. We'll use a 3/8 inch end mill to contour it. And then we'll use a spot drill to spot drill the holes. We will then use the drill to drill the holes. We'll ream this tight tolerance 249 to 248 hole with a .2485 reamer. And then we'll go ahead and chamfer the part right there. So that's going to be kind of the order of operations. Now remember, that's just for the first CNC operation. Check out this routing right here. The routing shows that the part goes from first to the saw, where it gets cut to length. In the first CNC operation, it gets everything profiled. Then it moves on to the second CNC operation. After that second CNC operation, we go to the final first article inspection. So let's go ahead now and start with that first CNC operation. When I look at that first CNC operation setup sheet, I see that my stock needs to be cut to a 3/4 inch length of cut. So I'm going to double check real quick with my caliper that my cut length is correct. So remember, you zero out your caliper, you go ahead and you measure your part, and you'll see I'm basically 7 thou oversized on this cut. We're not worried about 7 thou with that Sandvik face mill there. It'll take off that extra 7 thou, no problem. So now that I know that I've got the correct stock size, I'm going to go ahead and grab a file, and I'm going to file the edges of my part. Now when we cut this with a saw, the part has burrs around it, all the way around the outside edges. So I use my file to go ahead and deburr my stock before I put it in the vise. If I don't do that, it could sit not parallel to the bottom surface of that vise because it's sitting up on a burr. So we get rid of all those burrs by filing in one direction away from ourselves. And remember, away, file, lift up, return. And that's the appropriate way to use a file. It's not back and forth. It's away from you, lift, and return. So once I go all the way around the part, file it all up, I just double check with my finger. Oh, there's a burr right there. Just double check so you don't have any burrs. Now, we're going to go ahead and check out the soft jaw here. So come on over, and you'll see this soft jaw has been fully contoured. I'm going to leave my wrench right there. Now, the way this works, this vise works, is it basically only needs a half of a turn to open and close it. The rest is done by this ratchet system back here. So once I loosen it one time, I can go ahead and push down on the ratchet and basically move back and forth. So remember, to loosen it, you just have to push one side of it, and you slide back and forth. And this only moves a 1/4 of a turn. So let's first put it back here. This soft jaw has been custom contoured to go ahead and grab our round stock. So you're going to see when we put the stock in the soft jaw right here, we spread it around far enough and put it down in there, it's got a custom pocket that's been contoured to hold this 2.75 inch diameter stock. Now, we want to make sure that we deburr the edges like you see right here, because we don't want any of these edges to mislocate the part right here. Now, once it gets machined in operation number 1, there'll be this cam profile on the bottom of the part. This cam profile is important to keep the orientation on the part consistent for when I flip it from op 1 to op 2. So in the soft jaw, we machined a profile down here to go ahead and orient the part in op 2. So after we machine it in op 1, we'll flip it over and basically drop it down into there, and it'll orient itself in the appropriate location in order to get machined right there. But before we get to op 2, let me slide this back a little bit. Let's go ahead and learn how to appropriately load and basically tighten this vise. So what I like to do is I want to make sure I'm in the middle of my travel here on this. If this is hard to turn, you should not force it with this wrench. You'll end up breaking the vise. So you just want to make sure you can turn back and forth and have enough travel both directions. Once you do that, you put the part in the soft jaw and you pull this as far forward as you can so it clicks in. Let me show you. If it was back here, you would just click it all the way forward like that. And now I go to tighten my part by hand, and I use my torque wrench, and I double check that I'm at 10 foot-pounds of torque right here. And I make sure that I'm in the tighten position, so the lever's to the right. And I'll go down and I will tighten my vise like this. Now at that point, you're going to see that we have everything tightened. So now we put the torque wrench on here and we tighten till we hear the nice little click right there. Now we know it's been torqued. So to ensure that our part is fully seated down here, we go ahead and we take the dead blow mallet, we give it a nice little tap down, and we're pretty much ready to go. So the stock is loaded. I'm going to go ahead and close my door. I'm going to come up here and double check on my program that I've got Geneva Drive Wheel Op 1 loaded. I definitely do. I'm going to just read the rest of this. We have the correct stock size. We have the tool 1, height 121 for the reamer. That's correct. We have tool 3, tool 5, tool 7, and tool 8, and tool 10. So it looks like I'm pretty much ready to go here. So now that we've verified that everything is good in the machine, we're pretty much ready to go memory, reset, and cycle start, and start machining our part. Here we go. So this face mill is facing ahead at 48 inches per minute at 6,000 RPM. So we have optional stop on right there so we can show you what each tool path does. So that first tool path pretty much just face the top surface and level the playing field. Now we're going to bring in the 3/8 inch end mill to go ahead and rough and finish the Geneva cam. So this 3/8 inch end mill is set to a speed of 6,000 RPM. We're running 6,000 RPM. What surface speed does that end up being when this 3/8 inch end mill spins at 6,000 RPM? Can you reverse calculate that using your 4V over D equation? Go for it. Now that you figured out the surface speed, we are actually running 36 inches per minute for this end mill. If this end mill is running 36 inches per minute at 6,000 RPM and it's a 3-flute, what chip load are we actually running at? Remember, feed rate is equal to RPM times the number of teeth times the actual chip load. So solve for the chip load now that you know the RPM, the number of teeth, and so what this tool path's doing, it's spiraling in towards the center, and at a certain point, it's going to go ahead and start cutting the cam once it removes enough material right here, the Geneva cam. Now, when we look over here at the code, you're going to see that this code is just moving X and Y all in one tool path right there. The Z's are going to be the helixes down, where it's moving up and down. But these are simple 2-axis tool paths. Now at this point, it's going around the outside profile to go ahead and machine that outside diameter. Now that it's machined that outside diameter, it's going to come in and finish the profile that has that profile tolerance on it with the 3/8 inch end mill in that Geneva cam. All right. Now before we go on, let's check out the part. You'll see we've roughed out all the material and finished the outside diameter and finished that cam profile. So what's next is we're going to go ahead and grab that spot drill and spot drill the hole locations for the part. Now this is a critical operation because these hole locations have tight positional tolerances in reference to each other. There's 1, 2, and this one's a countersink, so it's going to be a big one. Excellent. So we have that countersunk hole now for the screw to sit flush for the handle. And we have the other 2 holes ready to go ahead and ream it. So you can see that right there. So now that we got the hole spotted, we're ready to go ahead and get the C-size drill out and go ahead and drill the hole for the ream. Now reamers don't like to take off more than about 1/10 thou of material. So this C-size drill bit has been selected to go ahead and drill the hole for that .249 hole, the .249 or the .2485 reamer. So what size is that letter C jobber drill? Look up in the drill and tap chart and tell me how much actually are we taking off in order to get from the C-size drill to the actual reamed hole size. But now that we got that hole drilled in there, you can see that, we are going to go ahead and we are going to move on to the F-size jobber drill to drill the holes. Now that C-size drill, actually we're moving on to the reamer now. I forgot, we got to ream the hole. So here we go. We're going to ream that hole with that reamer. It's going to be a nice round hole. We're not going to show you that one because it was literally just taking off about 1/8 thou of material. At this point, we're grabbing the F-size jobber drill. F-size jobber drill drills straight through the part right there, no pecs. And we're going to go ahead and open that up and show you that all the holes are now created in this part. So what's next? We got to go ahead and make sure we don't cut anybody when they hold on to our Geneva Drive Wheel. So we're going to get that tool 5 out again, that spot drill, and chamfer the entire part. Now that the program's all done, we switch back to the original tool, so it's ready to go again when we load up some more stock. Bring the table forward for the operator. I'll open the door and we'll see how we now progress to the next CNC operation. So I'm going to grab my torque wrench. I'm going to go ahead, I'm going to open up the vise. And remember, I just did a real quick turn and I slide the vise backwards to pull the part out. So you're going to see there, we now have the full profile of the part machined right there. You see that? So we've got to go ahead now, flip it over and get rid of all this extra material on the top so we can make that little 3-axis hump. And we can see the difference between 2-axis and 3-axis tool paths, like I showed you in the programming stage in the CAM presentation video. So in order to orient that correctly, remember our soft jaw is going to grab this cam and orient it appropriately in the machine. So let me put back that part. We're going to come back over here. I'm going to just move the vise over a little bit so we can see it better. And what I'm going to do is I'm going to put it down here in the soft jaw. You're going to see that it locks into the correct position right there. You can't twist it anymore at this point. I pull that forward and then I hand tighten my vise. At this point, I'm going to grab my torque wrench, put it onto tight, and torque down my part. Once I torque it down, I like to use the dead blow hammer to make one tap on the part so it fully seats in the vise. Then we'll close the door and we'll come over here to the control, and when I hit list program, I can now move over to my Geneva Drive Op 2. When I select that one, I come down here and I hit select program, and then when I hit memory, it says Geneva Drive Wheel Op number 2. Stock size machine Op 1 blank, we got that. And we got tool 3, 4, 5, 6, and 10 now. So we're gonna go ahead and use the 3/8 inch carbide end mill to rough away all that material off the top. We're gonna use the 1/4 inch 2-flute ball end mill to go ahead and do 3-axis work on that protrusion sticking up with the fillets on it. We're gonna then use the 5/8 inch spot drill to go ahead and chamfer the holes and the outside of the part. And then we're going to use the 1/8 inch 2-flute ball end mill to engrave the best major in the world, manufacturing engineering, on the part. So here we go. Cycle start. So at this point, we'll go ahead, check that out. You see, we see the hole from Op 1 right there, but we've now faced it down to the appropriate height. Now that appropriate height isn't the height of the top of the part right here, it's actually the height up here. So we faced it to this height. Now we're going to use the 3/8 inch end mill to rough the rest of this other material away. So here we go. So these are reduced fees and speeds compared to what we normally would run out in industry. This is about 5 times slower than what we would normally run because it's our it's our second CNC machining lab that we're doing. All right, so that basically roughed out. That was a 2-axis tool path. So it moved down in the Z and then moved in the X and the Y, and it roughed out the big amount of material needed to go ahead and now use a ball end mill to go ahead and finish the 3-axis milled surface. So we're going to use that ball end mill to rough and finish now the 3-axis surface. Here we go. All right, now you can see it. Let's check out the screen right here. You'll see there's XYZ moves on every single line of code right there. In fact, it's verifying that it's at all those locations with that encoder. It can think, or it can process data faster than we can even think. So now check out this code right here is making a move up and down the sphere right over there with those 3-axis moves. All right, so our last step now is to go ahead and basically chamfer all the different holes on the outside up there with our favorite spot drill. I think I said last step, but really the last step is to put the logo on it, right? Manufacturing engineering. So this engraving is only going 2 thou deep. That's 0.002 inches deep. All right, now we'll switch back to the original tool. And we'll go ahead and bring the table forward. So at this point, we're going to go ahead and open the door, slide our code. Check it out right there. Go ahead and grab our torque wrench to loosen the vise. Go ahead and loosen that vise up. Remember, just half a turn, and you push down on the little slide right there, and you pull the part out. So what we've got here is we've got our 2 operations Geneva Drive Wheel, where this side was 100% just 2-axis tool paths. We flipped it over, did mostly 2-axis tool paths until we had to do this 3-axis surface right here. You can see the ball end mill went up and it followed the solid model. You saw that when we were programming it, and cut that actual surface. And what you're seeing are the little cusp heights for the step over in the ball end mill. So the least amount, the less of the step over we have, the smaller the cusp height, the better the surface finish. Except there's a point of diminishing returns because time is equal to money, right? So it's how smooth do you want it and how much time do you want to spend on it, right? So this is our Geneva wheel. We now need to go ahead and take our engineering drawing and bring it over into the inspection lab to inspect these true positional tolerances. So join me over in the inspection lab, and we're going to go see how close we are on our true positions from the B datum to this hole, and then our true position for the outside diameter to the actual B datum. I'll see you soon. Welcome to our Geneva Drive Wheels first article inspection demo. Today we're going to learn how to calculate the positional tolerance for this hole and this outside diameter relative to the B datum right here in the center of the part. So when we look at this engineering drawing right here, we see that the main datum is the B datum. The A datum is the bottom surface of this part, so the B datum right here is this 257 hole. Everything rotates about this 257 hole. That's why it's the datum. It's the main feature on the part that everything relates to. Now, in order for the Geneva Drive Wheel to drive the Geneva wheel, there's a pin located in this upper hole up here, which we call the C datum. We'll talk about that here in a minute. But this hole is going to be positioned relative to the B datum, basically perpendicular to A right there. So we're going to check to see if this 0.249 to 0.248 hole is first in size. If it is within the size limits, we're going to calculate the positional tolerance and make sure it's within the 7th diameter tolerance zone that it needs to be within for the design to function appropriately. So after we do that, we're then going to check the outside diameter of the part, the 2.725 inch diameter, and make sure that that positional tolerance is within 2 thou of the B datum there when it's at its maximum material condition. So we're going to go ahead and do that on our optical comparator. We wouldn't be able to do this by measuring it with a caliper unless we had some sort of fixture to show us the delta X measurement and the delta Y measurement from true position. Let me explain that a little bit better here. So when we have a positional tolerance measurement, we're measuring how far we're off from true position. So for example, if I looked at my drawing and I saw that the datum right here, A, is at this point, I will have a basic dimension locating the true position of a hole off of that datum. So there'd be a basic dimension on the drawing here, there'd be a basic dimension on the drawing here in both the X and the Y axis. When you go to actually inspect the actual part's location, you'll see when we manufactured the part, let's say the center of the hole was placed right here. Well, what we've got to do is we've got to determine how far we are off from true position in the X-axis and the Y-axis. And to do that, we're going to first set up the optical comparator over here to zero it out on the center line or the center datum on the part. Then we'll measure the hole's location and we'll determine how much delta X and delta Y we have from that. So we'll get the actual part measurement there, and then we'll do a simple calculation using the Pythagorean theorem to figure out this radius value, and when we multiply that by 2, we end up getting the diametrical tolerance zone, or the actual positional diameter that the part has. And we will compare that to the actual tolerance on the engineering drawing right here and make sure that we're under that size. So let's go ahead and do this. So remember, we're filling out this first article inspection sheet as we go through here. So looking at that first article inspection sheet, we're going to first find the feature ID A, the center datum hole size. So let's do that real quick. Now, this is an optical comparator right here. This is a stared optical comparator. Just so you know, cost, it was about $30,000 in 2015. It's got a control panel over here that can calculate radii, circles, distances, and angles out there in space. And the whole principle of an optical comparator is to magnify your part. So there's a set of lenses in here that can be replaced. You can get 25 times magnification, 10 times, 5 times. You can get different magnification levels. I believe what we have right now is a 20 times. It says X20 right here. So the way it works is there's this lens right here. When I turn the power on, I have a surface and a profile light right there. What that surface and profile light does is it allows me to either look at the surface of the part magnified or a profile of the part. I want to go ahead and look at a profile of the part because I want to look at basically the holes. It'll be a black and green image. Wherever there's a hole, it'll be green. Whenever there's material, it'll be black or a shadow. Now, you're going to see we're going to have to fixture that right here in order to measure our part. Now, we're going to first place this parallel bar down on the vise, because we're going to locate this part on the cam profile right here. So right here, we're going to actually set it down on this cam profile, which will orient it in space the way it's supposed to be oriented on the engineering drawing. And at that point, we can then focus it and figure out where this center hole location is. So to fixture this, I'm going to put it down on the optical comparator in the vise, make sure it sits nice and flat on my parallel, and then I tighten my vise down so my part doesn't move. Now you'll see up here on the screen, I can see some of my part. Now the way it works is there's handles right down here. So see, this handle is technically the y-axis. This handle right here is technically the z-axis, back and forth. X-axis, sorry. Z-axis is focus, that's what I was thinking about. So the focal length is the z, x is this direction, y is this direction on this machine. So our goal is to find the center hole first. So let's move it over. That's the upper hole. So we'll go down. And we want to go ahead and line up the crosshairs in the center of this hole right here. So you'll see I center my part, or I center it right there. And now I want to get a nice, good, crisp image of this hole. So you can see I can move the z-axis right here and I'm focusing on this hole. In fact, I want you to take a really good look at this hole. This one was manufactured with a drill bit. Do you see how this hole isn't very round? We're going to actually look at a reamed hole here in a few minutes, and you're going to see, you see how it's very jagged on the edges right there? So that's a drilled hole. It doesn't have a very good form compared to a reamed hole. But because that's where I want to zero out the machine, I'm going to now come over to the control right over here. This control says stare it. When I go ahead and I press enter, it has zeroed itself out right wherever I first start up the machine. I can zero it out by pressing these buttons right here anywhere I want on this machine. Now, whoever was using it last, it was me, left 3 different measurements in there. So I want to delete the measurements from the last person using it. To do that, I simply hit menu, I hit the button down here that says clear, and I hit clear all. And it says, do you want to clear all these features, datums, and SKUs? I hit yes. So now we're 100% cleared out. And remember, our goal is to go ahead and figure out the location of everything based off the center line axis of this datum, or this hole. So we're going to locate this hole and then zero out the control at that 0 point. To do that, I've got to go ahead and find the center of a circle. So if I press this circle button right here, it's going to ask me for a minimum of 3 points. It only takes 3 points in space to determine the diameter or a radius of a circle. However, the more points you give this machine, the better. So I'm actually going to give it 6 points so I can get a little bit, so I can be a little bit more accurate, right? Get a little bit more data, a little bit better calculation. So the way this works is, in order to pick points, I've got to line the crosshair up on the edge of the part, all the different edges. So I'm going to work my way around. I'm going to just move over here. I'm going to line it up. When it's lined up, I press this enter button right here. And it's stored 1 point. And I'm going to slowly work myself around. The more accurate you are lining up those crosshairs, the better measurement you're going to get. So I just press enter again. So move my way around. Press enter one more time. I've got 3 points. I can stop here, but I want to make sure that this is a pretty accurate measurement. So I'm going to grab 6. I'm going to grab more, 2 times what I need. Spend as much time as you want gathering measurements. So I've got 6 points. When I'm happy with the amount of points I've chosen, I hit the finish button right next to enter. Now if you look, it's a .2604. So on this part, I'm like right on tolerance, 260. I'm 4/10 out technically. It's most likely my points that I picked really quickly, because I actually measured the part before, and I got 259. So again, but this is what I'm going to put down on my inspection report. This is what I've got right now. So we're basically at a 0.2604. We're 4/10 out. We could technically measure it again, but we're going to just keep going from here because this is about learning how positional tolerances work, right? And if our part's bad, our part's bad. We can make another one. So right now, if we look at this screen, it shows me the diameter, 0.260. When I look at the drawing, the part has to be anywhere between 257 plus 3 thou minus 2 thou. So we're at 260. We're 4/10 over. We're going to call it good and just keep going. So now, I want to go ahead and zero out this so everything is based off of the datum B right here. To do that, you're going to see I'm -1 thou and 3/10 away in the X, and I'm 4 thou and 8/10 away in the Y. So when I press down arrow, it gives me the coordinates that I'm currently at. So I'm going to move it back to 0, where 0 is. So I was -1 thou and 3/10, if I remember right. There, whoops, there it is. There it is, and I'm going to 0 it at that point. Now I'm going to move my X down, or my Y, sorry, and I think that was 4 thou, if I remember right. 4 thou and 8/10. We can always go back and double check afterwards. So I'm right there. If I hit 0, now if I press upwards, you're going to see my new position in that circle is based off of where I just origined it out. I'm 1/10,000th of an inch off, right? So I'm literally going to go down, and I'm going to go -1/10. I think it was -1/10. And I'm going to hit origin there. Now when I go back up, I'm at 0, 0 for my circle. So I've now set the datum on the optical comparator. I can relate everything to the datums now and figure out my delta X and my delta Y values in order to calculate the true positional tolerance of the features on this part right here. So let's go do that. So the next thing we're going to do is we got to find this whole location right here. So I'm going to crank the optical comparator down, which moves up, right? So if the part goes down, we go up. It's a little bit opposite, right? So here we go. I now have the other circle in my sights. The problem is the circle is not in focus. The reason is it's got a different focal length compared to where the center of the circle was. If we look at the engineering drawing right here, our focal length last time was at the beginning right here. We now need to adjust our focal length that's inwards a little bit by adjusting that Z-axis. So to do that, I move this dial right here, and I get a nice crisp image of that hole. Can you see the difference between a ring hole and a drilled hole? I definitely can. Do you see how perfectly round this hole is compared to the actual drilled hole? You don't see any little lumps or anything like that on the sides of it. So hopefully we'll get this one in tolerance. Let's check it out. So now that I'm here, I want to go ahead and measure a circle again. So I'm going to click on circle, and I'm going to grab 6 points this time again. So moving over, I move over to this 1 point. I press enter. Come over here, I'm going to go up this time. Press enter. Move over. Enter. Enter. It's backwards compared to a regular machine. That's why you see me going backwards. It's mirror image. Enter. Now maybe one more at the bottom. We'll grab 7 points on this one. So when I hit finish there, I get 0.2495. So looking at the drawing, we're supposed to be between 0.248 and 0.249. We're 5/10 out on this one too. Who knows? This thing might be out of calibration. It hasn't been calibrated since 2015 when it was purchased. But by the Stereotech, he came in and calibrated it. But again, I'm pretty happy with that. So we're going to go 2495. So let's check out these other numbers here. And let's see how they make sense with our engineering drawing. So when I look at that, this hole is at 0.2495. But it is -3/10 out in the X. So it is off position by 3/10,000ths of an inch in the X-axis right there. Now in the Y-axis, it is 1 inch and 4/10,000ths of an inch away from the actual datum. But when I look at the basic dimension right here, you'll see that it's got 1 inch. So I need to subtract that 1 inch basic dimension from the 1 inch and 4/10,000ths of an inch, and I get a positive 4/10,000ths of an inch right there. So I'm 3/10,000ths out in the X and 4/10,000ths out in the Y. We're going to go ahead and calculate how that works here in 1 second. But we're going to get the rest of the measurements first, and then we're going to come out and we're going to calculate it together. So I'm going to write that data down real quick. I was right here, my negative X, or my X, I was 0.0003, and Y, I was basically 0.0004 out right there. So that's my delta for basically the 0.249 diameter hole. So we're going to use that in some math, but before we do that, I want to grab the other positional tolerance right here and the diameter D before we go on and do the math together. It's easier to do everything on the machine and then jump into the actual chalkboard over there, or the whiteboard over there, and do some math. So the next thing we've got to do now that we've got that measurement down, I'm just going to write down my measurement as well, just so I have the diameter. 0.2495 was the diameter, just to have it in my notes right there. So the next measurement is outside diameter. I'm not going to be able to get down to all the points around the bottom there. I can get most of them though. I can get very close to almost all the way around the part. Doesn't matter though. I'm going to grab 4 or 5 points all the way around, and we'll figure out where we're at positionally against that B datum. So to do that, we got to call up another circle. So I hit circle. I move all the way out over here. And I'm going to just start right down here. You're going to see I'm going to come around tangent edge just because. And I'm going to call right there my first point. I'm going to press enter. I'm going to work myself up and around this circle a little bit. Just remember, the more points, the better. More data, right? So I'm going to line that one up right there, press enter, work myself around. I'm going to come right over here, enter, come back around up more, maybe come to the top of the circle a little bit, press enter, just come back over here, give it another data point, enter, come back around here, enter, enter. I got 7 points. Let's just go a little bit more. Enter, finish. So, looking at this one now, we are basically at 0.27243. When I look at my engineering drawing, we're supposed to be at 0.725. So we are basically 7/10,000ths of an inch out on our tolerance there. And looking at the positional tolerance, this one's a tight one because we're holding on to it, and we're in this second CNC operation, and we're relating basically all the features on that second side to this outside datum, which technically the reason we made it so tight is because we're holding on the outside, but the real datum is the B datum. So that's why we related these two to each other very with tight tolerances right there. So it's part of design, right? When you're designing something, you got to think about how you're going to manufacture it as well. Now, looking at this value right here, the X is at negative 6/10,000ths of an inch, and the Y is at a positive 4/10,000ths of an inch. So for the OD, the delta X is 0.0006, and for the OD, the delta Y right there is 0.0004. So what we're going to do now is we're going to walk over to the chalkboard, and I'm going to show you how to calculate the positional tolerance. Now that we're going to go ahead and we've got our data for our delta X and our delta Y measurements, we're going to use the Pythagorean theorem to determine the radius value of the positional tolerance zone. And if we multiply that by 2, we'll end up with the diametrical tolerance zone size. So we rearrange that by the Pythagorean theorem, so I can write positional zone size. That's going to be equal to 2. That'll go ahead and get us the diameter. And we go ahead and we take square root of delta x squared plus delta y squared right there. So to calculate the positional tolerance for that reamed dowel pin hole, we simply have our 2 square root. If I remember my number right, the delta x was 0.0003, so 3/10,000ths of an inch squared, plus, looking at my data right here, we had 4/10,000ths of an inch squared. So I got the calculator out here. I'm going to do it for you right here. I found this calculator in the classroom just now. So I'll take the square root, parentheses, 0.003, oops. Plus close parentheses. So we end up with a positional tolerance zone of 5/10,000ths of an inch for that diameter. That's pretty impressive, right? This is a brand new setup. Other than Brian, our department technician, and myself, no one else has ran parts on here. So it's making perfect parts. As people start to abuse the setup, that's when things go awry and tools start to get worn down. But let's just do one more calculation now for the positional tolerance on that outside diameter. So the outside diameter, so this is for basically the dowel pin. The outside diameter one, I'm going to write OD, basically tolerance zone, is going to be equal to 2 square root. If I go back to my data, the OD's x was 6/10,000ths of an inch, 0.0006 squared, plus we have the OD's y is 4/10,000ths of an inch. So let me grab my calculator now and go through here. We end up with 7/10,000ths of an inch, basically positional tolerance zone. So that's the diameter of the outside, or that's the diameter of the positional tolerance zone for the outside diameter, and then this one right here was the diameter for the dowel pin. Hopefully now you understand why positional tolerances are so beneficial in manufacturing. They give us 54% more area to locate that feature within that part. That's a bonus right there for manufacturing. And they allow us to hold material conditions, or hold tolerances at specific material conditions as well. We didn't do that in this example today, but we're going to do that in upcoming lab examples with the Geneva wheel. So join me for the other lab examples. I can't wait to show you more about GD&T. Have a great day. All right, now that we've inspected our Geneva wheel after machining it through both CNC operations, it's time for final assembly. Final assembly involves a press fit for this small little dowel pin right here. See the small little dowel pin? It gets press fit into this hole, and it ends up sitting flush with this top surface. So to do that, I actually am gonna kind of slightly get the dowel pin started in the hole right here. Now, I'm gonna put it down on the press, and I wanna make sure that the press clears the cam. So you want to kind of just eyeball it, make sure that you're not going to squish down on the cam right there. Then we have this small little tool right there to kind of keep it aligned so you can make sure it doesn't slip out. We don't want you putting your fingers under the press right here and trying to press in this part. So when we have that pressed in, we now have our Geneva Drive Wheel fully ready to go. We're ready to go ahead and put it in inventory, and we'll bring it back out of inventory in week number 5 when we do the tolerance stack assignment and assemble the Geneva Drive Wheel assembly. Have a great day.